Today I'm going to talk about the security of fully decentralized machine learning. So yes, we are in the collaborative machine learning setting, meaning that we have a set of users. Every user has a local training set, and those users want to train a shared machine learning model using those local training sets in a private way, of course. Now, a very popular approach to solve this problem is called federated learning, FL, for hereafter. But FL comes with some inherent limitations. So in FL, we have this central server, a central aggregator that pivots the communication among all the users in the system. And so when the number of users increases, the server becomes a communication bottleneck, reducing the scalability of the protocol. And because we have this powerful central server that has almost full control on the training process, this supernode, if adversarial, can run powerful privacy attack on the users, such as gradient inversions that we are going to see later. So yeah, there is a very large body of work that is trying to sidestep this problem by getting rid of the server. And in general, we call this line of work fully decentralized learning, DL. And the idea here is that we don't have a server anymore. Users communicate with each other using peer-to-peer communication channels. And now, because there is no central aggregator, there is no communication bottleneck, but more importantly, because there is no supernode that has full control on the training process, users have more privacy because there is no supernode that can perform powerful attacks. And this is like the main argument that decentralized learning proposers use. Generally, it's a very good selling point. And so in the paper, we were asking ourselves if this was actually the case. To answer this question, we performed the first thorough analysis of this class of protocols. Our analysis is both in the semi-honest, passive, and malicious active security model. And in the paper, we introduce a batch of attacks, new attacks. Now, the fact that I'm here talking in front of you, that means that actually that is not true in most of the cases. DL protocols inherently boost adversarial capabilities, resulting in less privacy for the users. And in our analysis, we characterize what we think are the main causes responsible for the insecurity of this class of protocols. And these two factors are in contrast tension, and we call them local generalization and system knowledge. So starting from local generalization, the first thing we have to understand here is that now in FL, every user shares the same model, a single global model, and every given time step. Instead, in DL, every user has a different local model. And the problem here is how those local models generalize during the training. So DL uses a gossip-based communication process, meaning that a model update, in order to fully propagate in the network, must pass through multiple nodes. And the issue is that every time that a model update passes through a node, some of the information that the model update is carrying is destroyed because of the aggregation role. Now, while a local model is a function of all the local training set in the system, those local training sets don't have the same influence on the final local model. In particular, the influence that a user has on the model of another user is a function of the distance in the network, with the local training set of the owner of the local model having the most influence. In other words, we can say that the local model in DL almost always tend to overfit the local distribution of a user. Now, coming back to FL, in FL, we have a single model, and users contribute equally to this global model. And now, however, in DL, we have a set of local models, and every local model maintains more information about the owner of the local model. And this becomes when we start considering adversaries in the system. Indeed, if adversary has access to the system, the adversary has also access. Okay, there is something wanting in the slides. Has also access to the model updates that those users produce. And an adversary can use a model update as input for an inference attack in order to infer information about the training set of users. Now, because, as I said, in DL, the models are not well generalized, an attacker can infer much more information from DL local model update than what can be achieved in FL for the same identical setting. On the plot on the right, we have the example of a membership feelings attack. Now, this was local generalization, but local generalization can be solved. It's enough for the user to connect to more users in the system. In this way, we are reducing the pairwise distances between each pair of users. And when the topology is fully connected, we solve the problem. Because now, essentially, we reach global generalization, and DL essentially becomes equivalent to FL, no more local generalization. However, this comes with obvious problems. The first one is that now every node has the same communication complexity of a parameter server, and that's bad. But there is also a security issue, because now the attacker is collecting what we call system knowledge. And the idea here is that, very generally, every time that an attacker connects to a new user, the attacker gets new information about the system in the form of model updates. And when the attacker has collected enough information, can exploit this information in order to create even more powerful privacy attacks. In the paper, we implement this intuition, creating an attack that we call the functional marginalization attack. So functional marginalization attack. And the idea is that if the attacker has access to the local model, to the model update of a target and other model updates generated by non-target users, the attacker can use the information carried by non-target model updates in order to isolate the contribution of the target user in his model update. Essentially, what we are doing here is doing arithmetic in the parameter space in order to marginalizing out the contribution of the target user. Now, once that we have this functionally marginalized model, we can use it as inputs for membership feelings attacks. And because of what was said before, attacking this set of parameters allows the attacker to infer even more information about the underlying local training set of the victim. However, system knowledge has actually more pervasive impact on users' privacy. Indeed, in the paper, we show that when, in the special case where the set of neighbors, so the nodes that are connected to the target, so the neighbors of the target is a subset of the neighbors of the attacker, essentially now the decentralized user achieve, sorry, there is delay. So the decentralized user achieves the same adversarial capabilities of a parameter server in FL. This means that the the server can access individual model gradients produced by the users, but can also decide the local states of the users. In order to show that, we introduced new two attacks. The first attack that is simply called gradient recovery, and we show that if the attacker is able to access the model updates of the neighbors of the target for 2 consecutive rounds, we can use this information in order to extract the gradient that the target user used to create the model update, which is private information. And once that we have the gradient, we can use it as input for a gradient inversion attack, and the attacker can recover part of the local training set of a user, breaching the privacy of the user, of course. Yeah, there is something wrong with the slides. So another attack is something that we call the state override attack. The attacker here, the attack shows that the attacker can replace the local parameters of a user with a chosen payload. In order to do that, the only thing the attacker has to do is to wait for the model updates of the neighbors of the target, and then use this information in order to cast adversarial model updates. Then when the adversarial model update is ready, the server sends it to the target. And when the target uses it for the aggregation, essentially that aggregation results in the payload. Now, if the attacker wants to perform a privacy attack, the only thing the attacker has to do is set the payload to trap weights that are a set of parameters that forces the model to memorize the input when computing the gradient. And when the target sends back the model update to the server can recover essentially verbatim copies of some of the elements of the local training set, completely breaching the privacy of the user. So summing up, those attacks show you that the privacy in DL is a function of the underlying topology. However, any configuration we can have seems to provide less privacy than FL. Indeed, every sparse topology induces local generalization, making the model updates more informative about the local training set of the victims. While if we solve local generalization by increasing the density of the topology, now we are allowing the attacker to collect more system knowledge. And this system knowledge can be used to cast even more powerful attacks and reach the same capabilities of a parameter server in FL. Now, the difference is that in FL, we have a single server, where now in DL, we can have multiple adversaries with the same capabilities. That is not good. However, I want to stress that, yes, decentralization is the right thing to do in order to achieve privacy in collaborative machine learning, but our point is that this requires extra care. Indeed, there are a few main problems that must be solved. The first problem is preventing attackers from choosing their neighbors, but it's not clear how to achieve this without introducing a supernode that has control on the system. And another option is also use secure aggregation. However, in the paper, we show that current secure aggregation protocols are not working very well in DL. This concludes my talk, and if you have any questions, I'm here for that.
Thank you so much, Dario, for your presentation. Do we have any questions here?
I didn't get your last point about secure aggregation. I mean, what exactly do you mean here by secure aggregation? Like, for example, secure multi-party computation, or adding differential privacy to the gradients, or what is it and why it's not working?
Yeah, okay. With secure aggregation, we refer to a specific functionality. So secure aggregation comes from the FL literature, where the FL server gets all the model updates for a round, but instead of getting the individual model updates, it only gets the sum because of a use of multi-party computation protocol. You can do the same in DL, so every user gets only the sum of the model updates without seeing the individual model updates for each neighbor. And that would prevent every attack based on system knowledge. However, we show that if you apply secure aggregation, the standard secure aggregation that you use in FL, in DL, there are ways that we can evade it. So essentially, in order to import secure aggregation in DL, one has to develop secure aggregation protocols that are tailored for DL. That's the point.
Thank you so much, Dario, for your presentation. Okay, if we don't,
So you mentioned as a motivation for DL, you mentioned that like there's no privacy in the FL setting. But once you introduce secure aggregation to that setting, like what are the limitations then?
So I mean, segregation is not perfect. Indeed, we had a paper at CCS last year where we showed that secure aggregation is not secure. But yes, secure aggregation helps, but it's not the solution because still the server can access the sum of the model updates, plus it can decide the parameters of the users. So, I mean, FL plus secure aggregation is better, but it's not totally private.
Okay, and are there any defenses for like against the server in which it's setting its parameters? Can client do some local checks to avoid that? Is there some work on that?
You mean in FL or?
In FL, yes.
Yeah. I mean, in our paper in CCS 2022, we find attack and we propose a patch. So there is a patch.
Okay, thanks.
thank you everyone for coming to this session. Now it's time for lunch. Yeah.